This is for the core pure one. It's chapter 2, so it's on Argand diagrams, loci in the complex plane and stuff like that. I'm going to go over all the challenge questions in this chapter, as well as some other ones which I've just randomly picked out. So the first one, we want to find all solutions to this, and we're given this as a hint, right? So it's saying that we can factorize z to the 6 as this, so we'll do that. This is a difference of 2 cubes. Now, if you don't know what the formula is for the difference of 2 cubes, you can just say, well, if we know one root is clearly just going to be z equals 1, which means by factor theorem, one of the factors is going to be z minus 1. And so some quadratic in the form ax squared plus bx plus c multiplied by z minus 1 must equal this. It actually must be identical to this. So then you can just equate coefficients, and then you'll get that. Here I'm just plotting on points. So z equals 1, and then z equals minus 1 as a solution, which I'll put on as well. And then you'll as I was saying, you'll factorize it into this, and then this one here, and then this one here also factorizes. It's kind of just something that you might have to like just look at for a little bit and try and spot it. Maybe just think to yourself, oh, I'll just need to swap the signs, if maybe you've seen the formula before and just, you know, had a small idea as to what it's going to be. If you don't, that's completely fine, because you could do the exact same trick. So you could say that z minus 1 is a solution, so that means z plus 1 is a factor, and then multiply it by some quadratic factor, and then just equate coefficients to that, and then you'll get this factorization. Like I said, you'll have solutions of z equals plus or minus 1. There's minus 1 there. And then we've already found this one and this one, so we'll just use quadratic formula on this and this. So if we start with this first, you'll get these two solutions. Okay, so we'll just add them to our Argand diagram. Look something like this. I should really be putting imaginary axis and then real axis, but it's fine. I mean, you know what I'm doing. Same thing here, so just put into the quadratic formula, you'll get these two solutions. Just put those on the Argand diagram. And you'll see, well, that it lies on a circle actually. Okay, centered 0, 0, radius 1, which means that from any z, which is the point on the circumference of that circle, to the point 0, 0, there is a length of 1. Okay, I know that's a terrible circle. It's supposed to be a circle, but yeah, it's a circle of radius 1, as you can see. I've just drawn it a little bit better there, I think. So the second challenge question, we've got this z, and we want to show that z to the 7 equals k times z. So we'll just find the magnitude of this number. Now, if you plot it on an Argand diagram, you'll just see that you're going 1 across and then root 3 upwards. So it's just the square root of 1 squared plus a root 3 squared. And that gets you r equals 2, right? Obviously, you won't put minus 2 if this was a plus or minus square root, because the length is just always positive. And also, this is the principal root, so you just take the positive solution. Anyways, and then the angle that this complex number makes with the positive real axis is just going to be, well, if you're going across 1 and you're going up root 3, if you do inverse tan of opposite over adjacent, you'll get that angle there. Okay, sorry, tan of that angle equals opposite over adjacent, so you do inverse tan of opposite over adjacent. Actually, I think that's what I just said. So if you just do that and you solve for theta or arg z, they're both the same, you'll get pi over 3. You should just know your exact values, to be honest. And then if you put this in modulus argument form, also known as polar form, as you might have seen, it just r multiplied by cosine theta plus sine theta. We've got theta and we've got r, so you just plug that in. Now we want z raised to the 7, and a fact that you have to know from doing this chapter is that whenever you're repeatedly multiplying complex numbers, what you're actually doing is you're multiplying the modulus that many times, and then you're adding the arguments. Now you can prove this, and they do actually prove it in the chapter with the formulas for adding two angles and stuff like that, and you can try it yourself, but I've just put this like general idea here. So if we multiply z by itself 7 times, right, that's just going to be 2 to the power of 7, and then we're going to add 7 lots of pi over 3. Okay, so it's just going to be 7 pi over 3. Now, if we just take away 2 pi from both of these angles, you'll still keep the same thing, right? So it's just pi over 3 still. So the angle doesn't actually change. And then if you look at this, we want to be z to the 7 equals k multiplied by z. So if we split this into 2 to the 6 multiplied by 2, this 2 to the 6 is just 64. And then you'll notice that this part here is just z. Okay, and so k just must be 2 to the 6, which is 64. We're going to do a similar thing here for z to the 4. Okay, so what I did was actually I got z to the 7, which is just what I'd already done, and then I split this z to the 7 into z to the 4 multiplied by z to the 3. And then I divided by z cubed. Now, if I'm dividing by z cubed, I'm basically just taking away 3 powers away from this, because I'm just dividing this modulus 3 times by 2. Okay, so that's just dividing by 8 or just taking away 3 from the power. And that also means I'm going to be subtracting 3 lots of pi over 3. Okay, I actually didn't even notice this, but yeah, you should also know this from the chapter. So when you're dividing, you're just dividing the moduluses and then you're subtracting the arguments. So the angles here are going to be pi over 3 subtract pi. Okay, now I've color coded them just to make it a bit more simpler. Now you do get the formula for something like this and something like this, so you just use them. I have color coded it like I said, and with this you can actually simplify it a bit more. Sine of pi, or sine of 180 degrees, is the same as cosine of 90 degrees, which is just 0. So all of this goes away to 0. Now cosine of pi is the same as minus sine of 90 degrees, which is just minus 1. So this is going to be minus cosine pi over 3. If it shows up, yep. Okay, and then we're just going to do the same trick here with this one. Okay, so I've color coded it again, and let's just check. So sine of minus pi is the same as minus sine of that positive angle. So this is just going to be minus sine of pi. Now sine of pi is going to be cosine of 90 degrees, or pi over 2, and then cosine of 90 degrees is just going to be 0. So this entire thing just goes away. Okay, and then you're just left with this. Cosine of pi is just let me think. So cosine pi is cosine of 180 degrees, so that's just the same as minus sine of 90 degrees. So this just becomes minus 1 multiplied by sine pi over 3. And so I've just brought the minus up here, and I've just copied these. Oh no, never mind. I split up this this modulus here, right? Because if you look at this, we want to be multiplying by z, right? So we want to try and get this expression on the right hand side. So just ignore the equals and this part. We want to try and like shoehorn this into this. Okay, there's a couple of ways we can do that. This looks very similar to this except for the minus sign. So let's just factor out the minus. Okay, we'll put it in front here. And then you'll notice, well, this is the same as z, so we'll just replace that with z. And then 2 cubed is 8, and then it's going to be minus 8. Okay, so that means p is minus 8. Show these complex numbers on an Argand diagram and describe the relationship between them. Okay, so just write them out here. Z is this, as we've just said. All right, so if we just maybe put that roughly there, that's Z. Okay, Z to the 7. If you think about it, you're just increasing the length of it from the point 0, 0, right? And if we've increased it because we've multiplied it by itself 7 times. So this angle, they all actually make the same angle, same pi over 3, as we've shown here. So we've just stretched it. Okay, so the z to the 7 is somewhere up there. And then z to the 4, you can tell here it's actually, it's like we've stretched it, but by a minus scale factor. So we've actually stretched it backwards away in this direction. Okay, by a factor of minus 8. So it's going to be somewhere here. And because they all have the same angle, minus, except for this negative angle, I guess, right? They all just lie on a straight line. And so that's just the geometrical relationship between them. So we've got a complex number z, okay, and it's we've got z plus I has magnitude 5, and then the argument of z minus 2i is theta, where theta is a real constant, such that it's in this range. Given that z minus 4i is less than 3, okay, find the range of possible values of theta. One thing which I'm going to do just to make it a bit more simpler is just write it in the form z minus something. Now here I've actually put x for some reason. I actually don't remember why I did that, because I actually did make these slides quite a while ago if you look at the my upload history. Right, so you can just split this up into this. Hopefully you can see that this is the same, but this is just saying what is the distance. It's just saying that the distance between some general point x and the specific point 0 minus 1 is 5. Okay, so let's just plot that. So we've got any point x, okay, and then its distance from 0 minus 1, so 0 minus 1 here is 5. So we could have x be the point here, or here, or here, or here. And if you keep on going around, you'll just realize it makes a circle. And you should know this. This is something which you do get taught earlier in this chapter. So it's just a circle centered 0 minus I with radius 5. Okay, z minus z1 is the length, and that's that. What I've done next is I've said let z equal a plus bi. This is nothing new. I think in the chapter they actually prefer to use x plus iy, but it obviously doesn't matter. Let's change this z. Okay, we actually don't need to change it because it's already got the minus sign, but I'm just going to put brackets around it just so hopefully you can see, just so it looks a bit easier. This is the point 0, 2, so that's somewhere up here. Okay, and we're saying that the argument that it makes with just this parallel line here is going to be theta. Okay, and theta lies between pi and minus pi. Okay, so let's just say maybe it could be there. Okay, and this is the angle theta, and then this will be the point z. Okay, now theta can range, remember, so it could actually be, it could actually go across here. Hopefully that makes sense, because this is less than pi over 2, this is pi over 2, and then this is pi, so actually theta could go all the way across here. Not exactly to it though, because it's not inclusive. But yeah, that's that. Now for the third part, we've got another circle, okay, centered at 0, 4, okay, and the point z, which satisfies this, is just going to be everything inside of the circle, including the circumference. Sorry, not excluding the circumference. I've actually not done it dotted, now that I've just realized that. It doesn't actually matter, to be honest. You will drop marks if you don't do it dotted, but it must have just been difficult in PowerPoint or something. Anyways, this here is the other angle theta you could have, or you could just even say this part is theta here, because these two angles are just the same. Okay, and now before we carry on, I'm just going to explain why I've actually put the lines here. Okay, and why it's not just straight down like here. First of all, this question is just about restrictions. Okay, so everything in terms of loci diagrams is basically just about restrictions. Okay, we've got a point here, okay, which is 0 minus 1, and we're saying that the distance from any number z to this point here is going to be 5. Okay, that's fine. That makes a circle radius 5, because you can just have any point around it, and that satisfies this equation here. Okay, that as long as it lies in the circumference, obviously. Okay, we've got a half line here. Okay, and it makes an angle theta with a positive real axis. Okay, and it starts from 0, 2. Okay, now I could have put this line here anyway. I could have put it here. I could have even put it like straight out like this, but maybe actually no. But could I? It needs to be between pi and minus pi. So you could put it anywhere that's between pi and minus pi. So say I just put it here. Okay, so pi over 2. That it's not actually pi over 2. It's less than pi over 2, but it's still within that range. So say I just put it randomly there. Okay, and now before I carry on, I think to myself, okay, let's use the next piece of information. We've got a circle here, and we're saying that z, first of all, needs to lie on the circumference of this big circle here. Okay, it also needs to be such that the angle it makes with the positive real axis is theta. Okay, and it needs to lie inside of this circle here, right? Because it's all of the points less than it. So if we think of this as being the circumference, and then the point, the center being 0, 4, we just want to be less than whatever the radius is. So first of all, we want to be inside this big circle. We want to be we want to be on the circumference of this big circle. We want to be inside of this circle here, but we also want to be making an angle theta with a positive real axis. So if you think about it, we want to be the points here, because if we're here, we're on the big circle circumference, we're inside of this little circle, and we can also make an angle that is theta with a positive real axis. And now we just want to find what this angle theta is. Now, to find the angle theta, what I'm going to do is I'm just going to think in terms of Cartesian coordinates. So this circle here, centered 0, minus 1, radius 5. So that's just this. Okay, you should just know this just from regular A-level maths. And then the circle, also just with the same reasoning, is just going to be x squared plus y minus 4 all squared equals 9. Okay, and is that fine? Yep, okay, cool, that's everything. And now there's a nice trick here that I know. And it's if you have two circles and you want to find the line that goes through them, one thing you can do is you can just subtract the circles, like the equations of the circles. Because if you think about it, you're going to get rid of all of the x squared terms, and you're also going to get rid of all of the y squared terms. Okay, assuming it's positive and positive, obviously. And then you're just going to be left with some linear equation, which just must be a line that satisfies, it satisfies such that any point it shares the same x and y coordinates of those two circles, right? So if you just subtract two equations of circles, you'll get the line that goes through them. Okay, and if you do that, you'll get that, and you'll get 10y minus 15 equals 16. Obviously, y here will equal 3.1. Okay, and then x, if you just plug it back in using a calculator, you'll get this. Right, now, I've put here 1.1, and it's because if this is already 2 up, right, because remember, it's starting from 2, z minus 2i, and this here is 3. So from here to here, just in terms of y coordinate, is going to be 3.1. Yep. But from here to here is just going to be 1.1. So this length here is just 1.1. And then this across here is just going to be whatever this x is, because it's not offset by any amount. Okay. And now we've got this, we can just use inverse tan of 1.1 over this equals theta. So just plug that into your calculator, you'll get 0.37 radians, and that's the minimum angle. Okay, now the maximum angle is just going to be, well, this one here. Well, actually, it's going to be this full angle here, because you're going to be measuring from the positive real axis. So you can just do pi, take away this, and you'll get the maximum, which is 2.77. And so that means that theta lies between these 2 points, but it's not actually equal to those 2 points, because we want to be inside of this circle, and you're only inside of this circle when you've got strict inequalities like this. So the next challenge question, we've got these 3 sets here. Okay, this is just always draw a diagram, and then always put it into the form, so z minus something. So for example here it's z minus, and then it's brackets minus 5 minus 8i. That's less than or equal to 5. So that's just a circle, maybe somewhere there. Okay, I've done the same thing for that one and the same for this one. Okay, and what I've done is I've just found, if you don't know what this is a perpendicular bisector. And to be honest, if you're watching this video and you don't know what this is, you should probably look through the textbook first before you watch this. Just watch this video after you do the questions. Okay, so this is perpendicular bisector, so just find the point, in between them. Okay, and it's just, yeah, just find the middle point between this number here and this one here, and that's going to be minus 5 minus 8i. Okay, and that's somewhere there. Now, I know that your sketch probably won't put it on the circle, but hopefully you can see. Oh, sorry, never mind, ignore that. What I'd actually done here is I'd actually just put on this point here. I didn't realize I thought I'd actually skipped these steps, that's why I didn't actually explain it. But what I did is I plotted this point here, which is minus 8, minus 4i, and then I plotted this one here. And then I just said that this midpoint, which is this, obviously, is just going to be the line, is just going to be the point equidistance between them, right? And that's going to be minus 5 minus 8i, just from averaging these two points here. And that is just on the center of that circle. So hopefully you can tell that these 2 points are just going to lie in the circumference, therefore. And like I said, it's a perpendicular bisector, so it's just a line that goes through it like that. I know that I haven't actually explained properly what a perpendicular bisector is. I think I actually do explain it a bit better later on in the video, if my memory serves me right. Like I said, I've done this a while ago, so I can't remember everything that I've done. Anyways, z minus, and then it's minus 10 minus 8i. And then just obviously put the rest in. You can ignore this. This is just telling you that it's complex numbers. It tries to make it look complicated by using set notation, but you just have to like look at the important information. So here, just look at the part after such that, after such that, after such that. Okay, so the angle of theta that it makes with the positive real axis is going to be less than pi over 4 but greater than 0. Okay. Oh, okay, this is the equation of the circle which I've put down, and I can't remember why I put it down. Oh, actually, I'm probably just checking that this point lies in this circle, I think. So this circle has Cartesian equation this, and then I plugged in minus 10 minus 8i, so minus 10 plus 5 is minus 5, and then minus 8 plus 8 is just 0. You get 25 equals 25, so this point here actually lies on the circle. Maybe it's somewhere there, apparently. Now, we've got angle 0 just going across, okay? And then we've got theta, the upper bound, which is just pi over 4. Now, pi over 4 is just like the line y equals x, so every one that you're going across, you're going one upwards, one across, one upwards, one across, one upwards, and it'll look something like this. Now let's actually look. So what we need. Now we want to be inside of this bigger circle here. Okay, so that's currently everything inside of this big circle, including the circumference here. Okay, now if you look at this perpendicular bisector, we want the distance from this point to this point, and then this point to this point. We want them to be different. We want them to be such that the distance from this point to this point be less than from this point to this point. Right, this is what we're saying. That we're saying the argument, the length, from this point here to just some other z, needs to be less from this point here to that same z. Right, and the only way we can do that is if maybe we put z somewhere here, because the distance from there to there is less than the distance from there to there, clearly. Right, so that means we want to be to the left of this perpendicular bisector. So right now we're in this entire region here. Okay, and we want to be where is it? So for the angle part here, between 0 and pi over 4, so that's just going to be everything here. So in total, we're just going to be this place here, except, right, if you look at this, we want to be in A and in B and in C, but the problem is here, it says C complement, so it just means not C. So instead of this point here, you just need to self, okay, all of those other conditions, which we've already said, minus this point here. So that just means it must be this place here and this place here. I think this is the last challenge question. Okay, so like I said, same thing, z minus, and then this thing in brackets, so that's just going to be 3 minus 3i. Just be careful, minus, make a positive. And we've got minus pi over 4. So that means the angle it makes with the positive real axis is going to be pi over 4, but it's actually going to be in the clockwise direction. Okay, so let's just sketch this. Okay, so it's gonna look something like this. I should have really put a dotted line like parallel to the x-axis, but I didn't. It's fine. This point here is the point 3 minus 3. Okay, and we're told that the complex number w is such that w minus z equals 3. Okay, so that means there's some complex number w which could lie anywhere on this Argand diagram, but we want the distance from any z here, and all z lies on this line, by the way, to be a distance of 3, exactly 3. So, for example, we could put w here. Okay, and the distance from there to there would be 3. Okay, that's fine. So w could be there. W could also be here. Okay, it could also be here. This distance here is 3. If we pick, say, maybe this point here, w could also be 3 over here, or this point here, w could be, oh, actually that one there. Just if you just go across, right, just across this line, the distance from any point from some point on this line outwards, if that distance is 3, that is the point w, and that means that's fine. We can include that. So if you just go around, you'll just eventually get that it looks something like this. I know this is a terrible drawing, but you get it, hopefully. Hopefully you can see that 3 across here is just going to be touching these axes. Sketch locus of w done. State the exact minimum value of w. Now, careful, this says w minus 0, technically. So it's just saying from the point 0, 0 to w, so any of this red part here. When is that minimum? Well, it's clearly just going to be from here to here. Okay, now if you think about this full length from here to here, right, this is the point 3 minus 3i. So we're going down 3 and we're going to cross 3. Okay, so that length there is just going to be 3 root 2, just using Pythagoras. So square root of 3 squared plus 3 squared, it's going to be 3 root 2. And then we want to actually subtract, that's the length from here to here, by the way. And now we want to subtract this length here. And we know that length is 3 because we've just said the point length from W to Z is going to be 3. So that's going to be 3 root 2 minus 3, and that's the minimum value of W. Okay, so now on to just some exam practice questions. Okay, so the locus of points representing this is a perpendicular bisector. Okay, so just draw down a diagram and then put the minuses in, as you should always do when you first start. You've got 3 minus I and then 1 plus I. Okay, so just put them in. I've actually put this on a Cartesian grid. It's fine, I think. Okay, now, okay, so we want some point here, Z. So let's just start without actually considering this. So Z can be literally anywhere on this diagram. Okay, and now we've said, well, the distance from Z, the distance from this point to Z has to be the same as the distance from this point to that same Z. Okay, that's what it means for these to be equal. Okay, so let's just pick, first of all, Z. The most trivial place for Z to be is just, you know, the perpendicular bisector, that same point right there, because now the distances from here to here and then here to here are equal. Okay, we could also pick Z to be here maybe, because the distance from here to here and then here to here is equal. We could also pick Z to be here, and then the distance from here to here is the same as the distance from here to here. Okay, and you can do it also in this direction, and then you carry on and you carry on and you carry on, and you'll just notice, well, that just means it can lie on any point here, right? And that's just the perpendicular bisector. Okay, so that's where this actually comes from, and why this is a perpendicular bisector. Okay, so that's fine, we've established that, and that midpoint is just going to be just averaging out those 2 points there. You'll get 2, 0. So I've just done 1 plus 3, which is 4, divided by 2, and then 1 plus minus 1, which is 0, divided by 2 is 0. Okay, that part's done. Locus of points representing Z minus 2 equals 2 root 2. Okay, just imagine this as, wait, why have I gotten the gradient here? Okay, I've just shown that I've just found the gradient of the perpendicular bisector. So this is just the gradient between these 2 points, and then the perpendicular bisector is going to be negative reciprocal, so m equals 1. And so this line must have equation y equals x plus c. And then if you just plug in the midpoint there, which lies on that line, you'll get y equals x minus 2. Did we even need that? Oh yeah, it does. Oh, didn't even read that. The question said find the Cartesian equations of it, so that's why I've done that. Anyways, locus of points representing Z minus 2 equals 2 root 2. Okay, so that means we've got some point here. Okay, remember, it looks like this. It's got coordinates 2, 0. Okay, and we want the distance from some random Z, so anywhere on this diagram, to 2, 0 to be the length 2 root 2. So that means it's just going to be a circle, radius 2 root 2, centered at 2, 0. Okay, looks something like that. And it's centered at 2, 0, so its Cartesian coordinates is just going to be x minus 2 all squared plus y squared equals whatever r squared is, so 2 times 2 is 4, times by root 2 squared, which is 8. So that's that. Find the 2 values of z that satisfy both this and this. Let's just draw them back on. Now you can tell, if we want z to satisfy this one here, so i.e. it wants to be exactly on the circumference of the circle, but we're also saying we want it to exactly be on this line here, that means the value of z which satisfies both of them is and, okay? It's just going to be this point here and this point here. We've already found their Cartesian equations, so let's just solve them. What have I done here? Not sure. What is this? I honestly can't remember what I've done here. The point is, okay, sorry, obviously, I was going to say, why haven't I written down the equation of this perpendicular bisector? I have, but it's just up here, and I've just forgotten about it. But obviously, so when two things are intersecting on a graph, you're just going to solve them simultaneously. So all I've done is plug in this y, so it's this equation of this line here, into here. So you have x minus 2 all squared plus x minus 2 all squared equals 8. This is 2 lots of that same thing. I divide by 2 on both sides, and then I square rooted, making sure I kept both solutions, so plus or minus 2. So that's plus 2 and that's minus 2. And then I'll get solutions x equals 4 and x equals 0. And so if you plug them back into any equation here, probably this one because it's the easiest one, you'll get y equals 2 and y equals -2, and that's these 2 points here. But careful, it says find the two values of z, so you want a complex number. So this complex number is going to be 4 plus 2i, and this is going to be 0 minus 2i, or just minus 2i. Okay, that's done. Now the region R is defined by the inequalities this and this. So like I said last time when I was explaining how to get the right inequality for a perpendicular bisector, I just said, well, pick a random point, and you want the distance from this point here, so 3 minus I, and this point here, 1 plus I, to be, you know, the same in this case here. But now we want the distance to be greater from this point, so that's 3 minus I, wherever that was, okay, somewhere here. We want the distance from some z to here to be greater than from that point there, or wherever that was, so that's going to be 1 plus I, so that's probably somewhere there. Okay, so the distance is going to be greater, so that means that point is going to be closer to this point here. Okay, oh, I've actually just put them back in. Okay, good. So we want to be to the left of this perpendicular bisector, because if we put z closer to this point here, you can clearly see that the length from z to this point is going to be greater than the distance from that same z to this point here. So we want everything to the left of this, including the point where it is actually equal. So including this line here. So that's just this there. That was a terrible animation, but that's R. And we also want to be inside of this circle, so 2 root 2. So that's that. The complex numbers w and z are given by w equals k plus I and z equals this, where k is a real constant. Given that the argument of w plus z is 2 pi over 3, find the exact value of k. Okay, let's just add w and k together just to see what this is going to be. If you do that, you'll get this. I've just clumped together the real parts and the imaginary parts, and then I'm going to plug it back into there. Okay. So just think about what this is. We're going across k minus 4 in the x-axis, and we're going up 1 plus 5k. Okay. If we're going across by some amount and we're going up by some amount, okay, we want to find the angle which that number makes. Well, it's just going to be inverse tan of the opposite side over the adjacent side, and this is the opposite side, this is the adjacent side, so it's just inverse tan of this over this, and that apparently equals 2 pi over 3. This means we can just do tan of both sides to cancel this inverse tan, and then we'll just have a tan on this. Okay, and tan of 2 pi over 3 is just minus root 3, I think. Yep. Okay, and then just multiply out on both sides, and then just be very careful here. You know how to solve this. I've grouped together the k's and then divided through. You don't bother rationalizing. You won't get extra marks for it. That's your answer. Given that the complex number z satisfies this, okay, remember this is a circle. Let's put it in z minus. So this is z minus minus 6 minus 6i equals 4. Let's just draw it out. Look something like that. Find the exact maximum and minimum value of the length, the z. Careful, this is z minus 0. So this is the point 0, 0, okay, here, to z. So that's anywhere on this circle here. And we want that length to be a minimum. Clearly, it's just going to be when it first meets it, okay? Oh, no, okay, I'm just showing you that it's that. So, for example, imagine we just said that z is here, okay? Well, the minimum value in this case is going to be this point here. Right, maybe if we picked it to be here, the minimum value is going to be here, and then we keep on going across, we'll realize, well, the only way that it's going to be a minimum is if that line actually goes through the center. Okay, now you can just pick points arbitrarily and just see by inspection, does it give me a minimum? And hopefully you should conclude that it doesn't, very clearly doesn't, unless you're like very close to going past the center. But anyways, yeah, it just goes through the center. That's just a fact that you have to know. And so here you can clearly see that the value of z, which has the smallest length from 0, 0 to that same z, is just going to be this point here. Okay, so we want to find the this point here. There are a couple ways we can do this actually. First of all, you can find the equation of this circle here, and then the equation of this line, and just solve it simultaneously. I think I was going to do that, and then I changed my mind because I thought there's an easier way to do this. and this is the way that you're actually taught it. So here we've gone across 6 and we're going up 6. Okay, so this line here is just going to be the square root of 6 squared plus 6 squared, which is just 6 root 2. So this full length here is 6 root 2. And then imagine if we subtract the radius, so 6 root 2 take away 4, you'll get this length here, which is the remaining length, and that's just going to be the minimum value. Okay, now the maximum value is going to be all the way over here. Okay, so this is, if this length here is 6 root 2, we can do 6 root 2 plus an extra 4 for the radius. That's going to be the maximum value. And that's that. Now find the range of values for theta, for which argz minus 4 plus 2i equals theta, and this have no common solutions. Okay, so let's just draw this out. Remember, put it into the z minus form, so just put in the brackets and then make this a minus. Okay, so we've got a point 4 minus 2i there. Okay, and we want its angle theta to not have any solutions. Now, first of all, what if we just draw out the line like this? Okay, and what if we draw out another one like this? Now, clearly, for it to have no solutions, theta has to be somewhere here, right? So it has to be this reflex angle here, and it has to be non-inclusive because we don't want any solutions. Okay, so one way that we can do that is we can find this angle here, and then we can do 2 pi subtract that to get this angle here. Okay, now just using GCSE circle theorems, we can see that the radius meets a tangent at 90 degrees. So this angle here is 90 degrees. This length here is just the radius, which is 4, which means we can find this theta here. Actually, we can also say that this length here is going to be 10, because minus 6 to 4, that's going across 10. Okay, and now we can find this angle x here, that's this minor angle. So inverse tan of inverse tan of 4 over 10, which gives us x. And that's that in radians. Careful, it is radians. And now we're just going to double it, because this triangle here is similar to this other triangle here that you could have made. Okay, so if we double it, we'll get this full angle here, and that's just going to be this long number. And here I've just shown it a bit better. Now we measure theta from the positive real axis. So if we just draw on and imagine just a random x-axis here, that's just a line that's parallel to the x-axis, and from where we're going to measure theta from, well, we could have this entire angle here, okay, excluding this part here, but we could also have this minus angle here. Remember, we measure counterclockwise. Okay, so first of all, theta can be less than pi. Okay, so that means it has to be here, but it can't be pi, because if it was pi, then that means we'd include this line, but we don't want to, otherwise we'd get a solution. So theta has to be less than pi, i.e. it has to be here, but it can also be greater than minus 2. Sorry, let me actually just write it out here, and it has to be within this range here, and ignore that for now, I've just not animated it properly. But where I've gotten this from, sorry about that, where I've gotten this from is, well, I've said, okay, if this angle here is just 0.3, no, it's 0.76 radians, and then I do 0.76 radians, so if I do 2 pi, take away that, I'll have this angle here, and then I take away the pi here, which leaves us with just this one here, which is going to be 2.38. And careful, I know that this angle here is positive, but remember, we measure counterclockwise. So instead of going around 2.38 that way, we want to go 2.38 this way, so it's actually going to be a minus angle. Okay, and that's going to be this angle here. And we want to be greater than that. And we don't want to be that, because otherwise we'd touch this and we'd have a solution. So the range for theta is that it's going to be less than pi, i.e. here, and it's going to be greater than minus 2.38, so here. Okay, and if we just put those together, you'll get this as your final answer. And that's everything. Thank you for watching.